Okay, so we're on section 9.3, and this is the second video which covers section 9.3 and section 9.4. There's a few tweaks for section 9.5, but this is the technique that you're going to use for every question on an exam, which is a Suvat equation, a constant acceleration equation question. And I'm going to use example 4 as my first example. But more than just a Suvat technique, you can think of this really as the technique for all of the mechanics, which is you're going to read through the information they give you in a question. It will pretty much every exam paper question on mechanics is going to be a worded question. It's going to be a paragraph. Your first job is to read through it and turn it into a diagram. Once you turn it into a diagram, you're going to work out which equations you need. You're going to write down the equation, the formula, and you're also going to write down what my old maths teacher called and what I'm still called a shopping list. So in this case, the shopping list is S, U, V, A, and T. Okay, those are the things that are involved in all that are Suvat, our constant acceleration equations. S, U, V, A, and T. They're all our variables. So we write down, we read the question, draw a diagram. Once you've drawn a diagram, you're going to write down a shopping list and a formula. For Suvat equations, you're going to write down the shopping list first and then the formula. Usually it might be the other way around. Then you're going to substitute from your shopping list into your formula. You're going to take all the information you know, put it in the formula, then solve your equation, and that's it. That's what happens in pretty much every mechanics question. Almost all, from here on in, almost all mechanics questions follow that broad outline. Read the paragraph, turn it into a diagram. Take the diagram, work out which formula you need, write down the formula, substitute in, and solve. Okay? Let's start with this example. A cyclist is travelling along a straight road. She accelerates at a constant rate from a velocity of 4 to a velocity of 7.5. And just checking our units, we're in meters per second and meters per second, so everything's looking good. We don't have to mess around with our units. So at this point here, we're going at a velocity of 4. That is our initial velocity, so I'm going to write it on as u equals 4 meters per second. Now, we haven't picked a direction as our positive direction, and I'm going to do that now. I'm going to say positive is going to be to the right because that's the usual way that we do it, isn't it? It seems most intuitive. At this point, I'm going with velocity of 4 meters per second in the positive direction, and I know the positive direction is this way, so I'm going to put a little arrow on there. They've put just a blob here. Remember, we're going to model our cyclist as a particle. We're not going to worry about the turning forces and the air resistance. So we're going to make that assumption even though it doesn't explicitly say it here. So that's where we're just going to draw a blob instead of bothering to draw a cyclist. We're thinking of it as a particle. She accelerates at a constant rate from 4 meters per second to 7.5 meters per second. So our final velocity is 7.5 meters per second. Now I know that is going in this direction because the question says velocity. It doesn't say speed, it says velocity. So if I'd turned around and I was going that way, there'd be a minus 7.5 in there. It tells us that the time equals 40 seconds, and we're interested in part A, the acceleration, part B, part A, the distance she travels, and part B, her acceleration. So distance, we're thinking displacement, aren't we? Well, if we say the zero displacement line is here, then the displacement at this point is the same as the distance we've travelled. Okay, so by this point in the exam, we've read it, we've turned it to a diagram, and we've realised it's a constant acceleration equation. So S, U, V, A, T, what do we know? There's my shopping list. Displacement, I want to know. Don't know, we'll put a question mark there. U is 4, V is 7.5 meters per second, meters per second. Acceleration, don't know. T, 40 seconds. Everything's in SI units, so everything's looking good. Part A asks us to find S. So for part A, I'm just going to put a big cross here, or you can cross it out if you want. We're not interested in acceleration. So looking at this, there are 5 variables. One of them's not involved in the question. I know 3 of them. I'm trying to find a 4th one. So I'm going to need the equation that doesn't have an A in it. And the way you pick your Suvat equations is you pick the one without the A or without the S, or whatever's not involved. So I'm going to need the equation without an S. Sorry, going to need the equation without an A. That is S equals U plus V over 2 times t. Now what I'd suggest you do is, until you know these 5 Suvat equations, stick them on one piece of paper and have that sitting next to you while you're doing all the questions. Once you think you're starting to get them in your head, then turn that piece of paper over, but leave it sitting next to you. And eventually you'll just find you've done 5 questions and you haven't looked at it because the equations are in your head now. But in your mental Rolodex, you're scanning through thinking, well, which is the equation that doesn't have an A in it? That's the one. So diagram, shopping list, formula. Stick everything in the formula. 4 plus 7.5 divided by 2 times by t. And that's it, right? And I'm not going to finish that off. It's in the blue box for you and you can work it out from there. Now the second part of this is asking us to find the acceleration. So let's go back. We've got the diagram here. We've got S, U, V, A, T. So I'm not going to draw a new diagram because I've got that. I could put, from part A, I found the distance and just checking it, it's 230 meters. So I could put that on my diagram before I do part B. So S is 230 and I found that in part A. A is what I'm trying to find, T is still 40, V is 7.5 meters per second, and U is 4 meters per second. So what do I need? I need an equation that's got an A in it, and other than that, I can use any equation I want, right? I could, now, that is true. The problem is S is something I found in part A. All the other information I got from the question. So it's best to avoid the equation, it's best to avoid an S if I can, right? So I need an equation without an S in it would be ideal, because if I got that wrong in part A, then I'm going to carry that mistake through. So I need to find A. I could use any equation with an A in it, except ideally I'll use the one without the S. So the one without the S is V equals U plus AT, okay? V equals U plus AT. Diagram, shopping list, formula, substitute in 7.5 equals 4 plus acceleration times 40. There's an equation with one unknown in it. Solve that and find the acceleration, okay? Now the acceleration, we're going from 4 meters per second to 7.5 meters per second, so we're expecting it to be a positive number, but it's taking us 230 meters and 40 seconds to get there, so we're not expecting it to be a particularly high number. And when we look at it, it's 0.0875 meters per second, okay? So every second that passes, our velocity gets bigger by 0.0875. That seems about right if it's going to take us 40 seconds to increase our velocity by only 2.5 meters per second. So that is the outline for any Suvat equation. I don't need to show you an example with the other 3 equations because it's always the same. Take the information you've got, turn it into a diagram, write on your shopping list. From the shopping list, decide which equation you want to use. If at all possible, pick an equation that doesn't, if you're on part B, pick an equation that doesn't rely on information that you found for yourself in part B. If at all possible, pick an equation that just uses the information from the question. Once you've got your shopping list, write down the equation, substitute in, and work from there. Now, there are a couple of other things. In fact, there are 3 other things to say. One is when we get to section 9.5, we're looking at page 146 here, and that's motion under gravity. That's a little bit difficult, not a little bit difficult, it's just a little bit different. So I'll deal with that in a separate video. The second thing to say is that they will tell you in the question 3 of these 5 bits of information. They might not make them easy to find. Right, so when I say they'll tell you in the question, they're not necessarily just going to say, oh, it starts at this speed, it finishes at this speed. You might have to read the question a few times. But if you've only got 2 of these pieces of information, that's not enough to do it in a single Suvat formula, okay? If they're feeling particularly malicious, they could give you some of this information and you end up having to write down 2 Suvat equations and solve them simultaneously perhaps, but even then, it's, you know, they have to give you enough information that you can make your equations work. So they've got to give you almost always 3 pieces of information, and you find a 4th piece of information. If you haven't got enough information, then go back and read the question again. Maybe there's something you missed. typically things that people miss are things like the displacement is 0 when t equals 0. So if they say you start from the starting line of a race, then that's telling you that as the gun goes off to start the race, the displacement is 0 as well. So t equals 0, displacement is 0, and velocity is 0 in the starting conditions. That's the sort of thing that might not be evident the first time you read the question. The way you get used to the harder questions is start with the easy ones, go through all the examples in the book, go through the exercises 9C and 9D carefully, and they'll build up to harder questions. If you go to the mixed exercise too fast, you'll get stuck. So don't do that. So I said there were 3 things. 1, vertical motion, we'll do that in a separate video. 2, the questions do get harder, and the way you deal with that is start with the easy ones, work up to the harder ones, and go back and read the questions if there's some information that you're missing that you think you should have. And the last thing is here in example 9, and it goes like this. If I've got an object that starts at O, and it starts with a velocity, let's just, well, I'm not going to use example 9, but the example 9 is an example that uses this idea, so you might want to go through that separately after this video. So we start from O, and we go towards A, and we start with a velocity of 10, okay? Now, if I have, let's say this is my positive direction, if I've got a negative acceleration, then that means, well, at the moment I've got a positive velocity, and negative acceleration is going to slow me down. It's going to be a deceleration. Accelerations, oh, by the way, I don't think I've said this, accelerations go on the diagram usually with a double arrow to show us it's an acceleration, not a velocity. And let's say the deceleration is, I don't know, minus 2 meters per second, okay? So every second that passes, I'm slowing down by 2 meters per second. So what's going to happen? I start off moving, and remember, everything is moving just in one dimension here. So I start off at O, I move towards A, I'm initially going at 10 meters per second, and I slow down, and then there comes a point where my velocity has got to 0, right? Now, if you were in a car or on a bike, and you braked, you applied a decelerating force, when you got to 0, what would happen then is you would stop and you'd stay stopped. But what's happening here is an acceleration is associated with a force. So what's happening is we're applying a force, and the force is acting to the left. It's acting that way, okay? So if the force is acting to the left, what happens to this object? Well, if the object is traveling to the right and the force is pushing it to the left, it's going to slow down and stop. If the object has stopped and the force is pushing it to the left, it's going to start accelerating in this direction. So what the motion is actually going to do this, it's going to go fast, slow down, and then it's going to get to here, and then it's going to start slowly moving this way, and then it's going to get faster and shoot off in that direction. So that is the motion that we're going to get. Now, I can't show that on the diagram by moving in one dimension. I can't go backwards and forwards along the same line because I can't see it. So what we do is we show that like this, okay? This object hasn't actually moved from up here to down here. There's no vertical difference, but I have to show the motion in that direction to start with, and then the motion coming back this way later on. So that is that's what we've got to do as a convention in our diagrams. Now, you've noticed that we have equations like v squared equals u squared plus 2as. Now, if you have a constant acceleration, and we were to say to this to the mathematics in here, well, when you are a distance of 2 meters away from your starting point, so now we know s, we know a, we know u, and we'd say, well, what's the velocity when you're 2 meters away from the starting point? Well, what we'd get there is v squared equals, well, let's work it out exactly. U squared is 100 plus 2 times minus 2 for the acceleration times 2, okay? So v squared equals 100 minus 8, so 92. So v equals, well, if v squared equals 92, v equals, and hopefully you're not going to fall into the trap of just saying square root of 92, it's plus or minus the square root of 92, okay? So what's that there? Let's call it 8.4. I'm just working off the top of my head. So plus or minus 8.4-ish, right? Roughly-ish meters per second. So which one do we want? Do we want plus 8.4 or do we want minus 8.4? Well, if we want the velocity the first time we hit this point, we want plus 8.4. If this is a situation where we've got something traveling that way and it has a force that pushes it backwards and slows it down, and then that force keeps going and keeps pushing it backward, keeps pushing it in the negative direction so that it comes back to this point here, well, in that case, both of these velocities are going to be the case. When it goes past it this way, we're going at a velocity of 8.4. When it goes past in this direction, we're going at the speed of 8.4, but a velocity of minus 8.4, okay? You have to be careful with your modelling here. If this is a car and it's slowing down because somebody's pressing the brake pedal, this part isn't going to happen. It's not going to start reversing just because you've got your foot on the brake pedal. If it's if the force that's making this thing move in this way is a different kind of a force, you know, maybe it's something that's I don't know, it's a toy car that's going in that direction, and somebody sort of pulls back with it on a string. Then once it's stopped, it's going to keep getting pulled by the string and going that way. If they keep the if they keep the force on the string such that the acceleration stays constant, that's what's going to happen there. Okay, so that is explaining the diagram and explaining why we sometimes get two answers. And it just is a case that you have to read the question and think about the context of the question, as well as doing the maths that goes with it. Main point again, read the question, turn it into a diagram. Once you turn it into a diagram, you should know that it's a Suvat equation at that point, or a constant acceleration equation. You're going to write down your shopping list, SUVAT. You're going to put into that shopping list all the things that you know, everything that the diagram tells you or the question tells you. You are going to write down the equation that you're going to use out of the 5 equations that you know. The way you pick the equation is you pick the equation that doesn't have the thing that's not involved. So if your question doesn't have an A involved in it, you pick the equation that doesn't have an A in it. You substitute into the equation, you solve the equation, check your units all the way through, make sure you're in SI units, and you're done.